Okay, guys, welcome back. This is our fifth lecture, and I hope you guys satisfied with the previous lectures. Well, seriously, it's still brutal out here today because of the early morning. I hope you are all throwing out. Weather like this is kind of like a stress test for us, right? In engineering and in life. You don't really know how strong a material is until you put it under some extreme conditions. So if you are feeling the pressure today, whether it's from the cold or from your coursework, just remember, endurance is a skill. It's not just about surviving the freeze. It's about knowing you can handle it. Let's get through this together. Before we wrap up, I want to address a common source of confusion that comes up when we start solving equilibrium problems. The sign conventions versus mass result. I want you to look at the slides on the screen. When you draw a free body diagram, you usually have to draw an arrow for the unknown forces. For example, Fn here. But since it is unknown, you may ask, which way do I point the arrow? Right? Which direction? Well, the answer is, it is an assumption. Look at the two cases on the slide. On the left, we assume the force was a tensile force, right? On the right, we assume it was a compressive force. Here, the coordinate system is local, only focus on the tension or compression. Now, notice what happens when we solve the equilibrium equation. Since the equilibrium equation is written in the global coordinate, right, that is the XYZ system, independent of tension or compression, we may get plus Fn on the left and minus Fn on the right. After solve the force balance equation, in the second case, the right case, right, we get a result of a negative 1 kilonewton. Does this mean the magnitude of the force is negative? Well, actually no, because the force magnitude are always positive, right? Because it's a magnitude. There's no positive or negative for the magnitude. Did you make a math error? Well, actually, no. A negative sign simply means the true direction of the force is opposite to the arrow you draw, right? Is opposite to the direction you assume. So, to avoid confusion and those kind of mathematical complexity during the exam, here is my golden rule. When you draw your free body diagram, always assume the force is acting in the positive direction according to our sign convention. For normal stress, that means we always assume the force is in the tensile direction. Draw your arrow pointing away from the car surface. Why do we do this? Because it makes the interpolation automatic. Right? If you find your final answer is positive, the magnitude is positive, it confirms your assumption. The material is under tension. If your final answer, your magnitude is negative, it corrects your assumption. That simply means the material is in compression. And compression, is negative, right? Because of the sign convention. By doing this, the math does this kind of sign convention for you automatically. Now that we have cleared up the sign convention and the ground rules, we are ready to dive into our first major topic of this semester, the axially loaded members. The definition is simple. These are structural components subject only to tension or compression. There is no bending and there is no twisting. The force acts directly along the longitudinal axis of the part. I want you to look at the examples on the slides. There are everywhere in engineering. Columns supporting a roof, for example, right? Steel cables on a bridge, or the hydraulic cylinders in machinery. In all these cases, the member is experiencing only tension or only compression. There is no bending, no twisting. Because the loading is so straightforward, this is the perfect place for us to start applying our new tools of stress and strain analysis. So, what exactly defines an axial load? The axial load is a force that is applied strictly along the longitudinal axis of the structural member. The load vector must be aligned perfectly with the center line of the body. I have also included a reminder here about our sign convention, right? Even though we just discussed it, it is crucial for this chapter. When you start solving this kind of problems, I suggest you guys always assume the unknown internal force is acting in the outward normal direction, which is the tensile direction, right? Assume your internal force is positive under our sign convention. Well, this means the stimulated is in tension. If you get a negative result and you know it's compression, it simplifies the math. Here, next, we need to make a very clear distinction between external and internal forces. Well, the external forces are the loads applied from the outside, like the weight on a cable or the reaction from a support. The internal forces are what holds the materials together, which is actually the atomic force, right? They act between the particles of the material. Here is a crucial part for solving problems. You cannot say internal force until you make a cut, right? Look at the diagram. We start with the whole bar. Always say other external force P, right? To analyze the stress, we have to image a slicing, right? Image a imaginary cut from MN, right? The cross-section MN. Once we separate the pieces, we must add an internal force that at the cut surface to maintain equilibrium. Otherwise, the material will go away, right? Because of the external load P. This internal force exists specifically to balance and counteract the external force, and this is the force we used to calculate stress. Because the stress is a measurement of the intensity of the internal load, right? Internal force. The stress is the magnitude of the internal stress divided by the cross-sectional area, right? So how do we actually calculate this internal stress or internal force? We use a technique called the method of sections. It is a three-step process, and it is the foundation for almost everything we will do in this course. Let's walk through it. First, visualize a cut plane MM passing right through the point you want to analyze, right? You are effectively slicing the object into two separate parts. Now, you choose one of those parts, right? After the cut, you have two, right? You just choose one. Let's say the left one, and draw it in isolation, right? Draw the free body diagram of this side. You keep the external force F, but on the cut surface, you must add the unknown internal force Fn. Remember our rule, right? Draw Fn pointing outward normal, assuming tension. Finally, we write your balance equation for that single piece. The sum of the force in the x direction equals 0. Then we can solve the internal force Fn equals the external force F, right? So Fn equals F. Now a common question is, does it matter which side I choose? For example, here we did the exact same process, but we keep the right side instead. Right? Last one we keep the left side. Right now we keep the right side. We draw the free body diagram. We assume intention, and we solve the equilibrium equation. The result is still actually Fn prime, right? I use a prime to indicate, okay, I keep the right side. Fn prime equals F. There is no difference. Whether you look left or right, the magnitude of the internal force is identical, and it always in tension, right? So it's exactly the same internal force. This gives you a strategic advantage during exams, that you always choose the side that is easier to calculate. If the left side has 10 complicated loads and the right side has only one, pick the right side, right? The answer will be the same. Now, let's apply the method of sections to a slightly more complex but very common scenario: the bars with intermediate axial loads. Often you won't just have forces at the end of the bar. You may have forces applied at various points along its length. The question is, how do we find the internal force in this bar? The answer is, we can't just find one internal force. The internal force changes every time we pass an external load. So the strategy is simple: divide and conquer, right? We need to apply the method of sections to each distinct segment of the bar. For example, the segment AB, segment BC, and segment CD. Let's start from the top with segment AB. We make an imaginary cut anywhere between A and B because they are constant, right? There's no difference for the force balance equation. Now, remember what I told you about choosing the easier side, right? If you choose the top side, we would need to know the reaction force at the wall, namely the point A first. Well, we haven't solved the equilibrium equation for the whole structure, therefore we don't have it right now. We don't know the supporting reactions at point A. So, but we know the other three forces, PB, PC, and PD. So let's just choose the bottom portion, right? It allows us to solve the problem without finding the reaction force first. Look at the free body diagram, right? As the cut, we have our unknown internal force, say N1, pointing up. Why is pointing up? It's because we always want to assume the unknown force, the internal unknown force, pointing outward normal, right? Outward means it points to the direction that is outside the object you are interested in. So your object is under the lower part, therefore opposite to the object you are interested in means you need to point upward, right? And well, in other words, you just assume it's this side, this segment is under tension, right? Below the cut, we can see all the remaining external forces, like PB in the upward direction, PC in the downward direction, and PD in the downward direction. We can write our own equilibrium equation, right? Because we don't have a horizontal force, therefore the force equilibrium only have one equation, that is vertical force balance, right? The sum of force in y direction is 0, right? Which is actually N1 plus PB minus PC minus PD equals 0. Remember, the equilibrium equation is always written in terms in the global coordinate, which is independent from tension or compression. It's actually in the XYZ coordinate. By solving this equation, we get N1, the magnitude of N1 equals negative PB plus PC plus PD, right? Right now, we don't know the magnitude of PB, PC, PD. Let's just keep it abstract. Therefore, the plus sign or the minus sign is already within the magnitude of N1. If that's positive, then it's in tension. If that's negative, okay, it's in compression. Well, actually, by solving N1, we find that the internal force in this section is just simply the sum of all the forces below it, right? We do the exactly same thing for the other segments. We move down to the segment BC. we move our cut to a point between B and C. Again, we look at the bottom part. Notice what changed? Right? Since you make a cut between B and C and focus on the lower part, the force PB is not above our cut, so it disappears from our diagram. We don't include it. Our free body diagram now only contains PC and PD, two external forces, right? Again, the equilibrium equation gives us N2 equals PC plus PD. It still be the sum of all the external forces in the opposite direction. Similarly, we analyzed the last session, actually the segment CD, right? We cut between C and D. Looking at the bottom piece, the only thing left is the force at the very end, PD, right? The mass here is trivial, right? P3 minus PD equals 0, which means N3 minus PD equals 0, which means N3 equals PD, right? Right now we have all the magnitude of N1, N2, and N3. Therefore, we can draw this magnitude in a vertical diagram, like the diagram on the right, right? Since right now we don't know the magnitude of PC, PD, and PB, we just arbitrarily pick one of the magnitude and draw it as illustration, right? So right now you have the distribution of internal load, right? Remember, internal forces along the longitudinal direction, and you draw this kind of figure. This case is very simple because the load is concentrated load. There's no difference between the load, right? Between two applied points, the internal load is there's no variation in the internal load, so you can draw it piecewise. Now we move from discrete points to the real world of distributed axial loads. In the previous example, the internal force jumped in steps, but what happens when the force is spread out continuously? Right? I want you to imagine a heavy steel pipe hanging from a drill rack, like the one shown on the slide. There are no external weight hanging off it. The load is simply the weight of the pipe itself. Now ask yourself, is the internal force the same at the top and at the bottom? At the very bottom tip, the material is holding up nothing, right? The stress as the external load is 0, therefore the stress is 0. At the very top, that section has to hold the weight of the entire 1 kilometer long, for example, 1 kilometer long pipe, right? The tension is maximum here. So unlike the previous problem, the internal force here is not a constant. It's actually a function of x. Let's break down the calculation for this. Let's break down the calculation for this distributed load using the method of sections. Please look at the slide. First, we define our coordinate x starting from the top and moving down. Right? We make a cut at an arbitrary distance x. This splits our pipe into the upper half and the lower half. Now we have a choice. Which side should we analyze? If you pick the top, look at the diagram. You have to include the reaction force as the ceiling, right? As a point, actually the force indicated by the capital W, right? Which is the weight of the total segment, and its magnitude equals small w times the length times actually the if you keep the top segment, the length is x, so it's w times x. And the internal force N of x is pointing downward, for example, right? We just assume, okay, it's still in tension. The math works. As you can see, the sum of force equals 0 leads to N of x equals small w times capital L minus x. Remember, when we calculate the overall weight, we use the whole length, right? The whole length is L. And And well, okay, yeah, we need to solve for the reaction force as a whole of the structure, because no matter we cut at where, it's just our nx is just a balance with our lower weight, the weight of our lower part, right? So okay, so we got the equation that negative w plus small w times x plus nx equals 0. So negative w is just the whole weight, right? And then we have the distributed weight has a length x and the internal force nx. The summation of this one equals to 0. We can solve for the expression for nx equals small w times L minus x, right? This is the way we thought of using the upper half. But look at the bottom part. If we choose the bottom part, this is much smarter. Why? Because there's no support reaction to calculate. You only have two forces: the upward internal tension pulling it up, and the downward weight of the remaining pap. The length of this remaining piece is L minus x. So the weight is simply small w times L minus x. Then nx minus nx plus w small w times L minus x equals 0. Then you get the same expression for nx. Finally, we look at the graph on the right. The equation tells us that the internal force varies linearly. So we have just to calculate the internal forces for two very different situations. For the bar with point loads, we got specific values for each section. For the drill pipe, we got a continuous equation, right? Continuous function, sorry. Now, starting at a list of numbers or an equation isn't always the best way to understand what is happening to a structure, right? If you list a lot of equations, it's hard for us to visualize it, to analyze the structure. We need a way to visualize this, right? This leads us to the actual force diagram, or sometimes we say it's AFD. An AFD is simply a graph that plots the internal actual force, whether it's in tension or compression, right? No, they're all the same, just by a plus or a minus sign along the entire length of the member. On the left, look at the bar with the intermediate load. Notice how the diagram looks like a set of stairs, right? That's a characteristic of point loads or concentrated loads. The internal force remains constant within each segment, then jumps instantly whenever we pass an external load. On the right hand, look at the heavy pap. Notice the difference? Is a smooth, straight ramp. That's characteristic of a distributed load, like the self-weight, right? The force changes continuously from the maximum at the top to 0 at the bottom. Let's go back to our fundamental formula. Stress equals P over A. Previously, we used this to calculate the stress in the entire bar, but there is a major assumption or a strong assumption hiding behind this kind of simple equation. That is the uniformity. When we write sigma equals P over A, we are assuming that the internal force is distributed perfectly evenly across the entire cross-section. For this assumption to hold true mathematically, the resultant external force vector must pass through the geometric center of the area, what we call the centroid, right? We will revisit this centroid concept later in the third session, the bending section, right? But right now you need to know, okay, only when the equivalent concentrated force passing through the centroid, it won't generate any bending moment. If the force is off center, it creates bending, and this simple formula breaks down, right? We cannot use sigma equals P over A because there is some moment inside, and the moment will change the distribution of the normal stress. That is why calculating the centroid using this integral formula is so important in statics, right? Because you learn lots of calculating the centroid moment of inertia in statics. However, in the real world, stress is rarely perfect uniform. It varies from point to point. So we need to update our definition to be more precise using calculus. Instead of looking at the whole area A, we look at a tiny differential area element, delta A. Right? This delta means infinitesimal. Right? The force acting on that tiny spot is delta P, which is actually an infinitesimal force. So the exact stress at a specific point is defined as the limit. In the limit case, right? Sigma equals the limit as delta A approaches 0 of delta P divided by delta A. It still be the force divided by area, but in this case, the area, right? It goes small until it shrinks to a point. This means the stress is actually a point function. It can vary along. It can vary at a surface or at a plane that we make the cut, right? If we want to find the total force P from this distribution, we have to sum up all these tiny stresses by integrating sigma over the area, right? Because sigma equals P over A, then P equals sigma times A. If the sigma is defined differentially, then we just integrate it. We can get the total force acting on this plane, right? Now you may be asking, why do we care about this limit definition? Why can't we just use P over A as a simple form? Look at the photo of the steel beam connection. In practice, real forces are never applied uniformly. They come from belts and welds, right? They are concentrated in specific, irregular spots. So if real-world loading is so messy and complex, is our simple formula sigma equals P over A an oversimplification? Are we get wrong to use it? Well, the answer is yes or no. We aren't completely wrong. It depends on which region we are looking for. And the reason why this formula is still acceptable is called Saint-Venant's principle. Right? Saint-Venant's principle is the engineer's best friend. It basically says, okay, the specific details of how you apply the load only matters locally. I want you to look at the three diagrams on the right. The case 1 is, okay, a concentrated point load. Well, the case 2 is actually a distributed load. Right? Case 3 is a perfectly uniform load. Notice that the rigid lines near the top, near the action point of the concentrated force, right? They are distorted, very differently. They are distorted, and it appears differently from top to bottom. Right? But look further down. Once you get a short distance away from the load, the grid lines recover to the regular case. It looks identical. They are straight and uniform. So this is the key takeaway. If you are sufficiently far away from the connection, usually a distance equal to the width of the bar, the stress distribution smooths out and becomes uniform. This is why we can still use sigma equals P over A for the main body of the member, right? Even if the connection at the end is messy. So the answer is yes or no because it depends on which region you are looking for. If you are looking for the region that is very, very close to the action point of the concentrated load, then definitely P over A is kind of averaged value is incorrect. But if you look at some region that is far away enough from the loading point, then it's acceptable. And for engineers, we want this kind of a thing as simple as possible. Therefore, we still use this kind of averaged value to help us make our life easier. Now, we need to make a step back and look at the big picture. We have spent a lot of time defining stress and strain. They are crucial concepts for us as analytics. But when you go out into the real world, when you are working in a design firm, your client or your boss isn't usually going to ask you what is the strain tensor or the stress tensor at point A, X. Right? Instead, they are going to ask two very practical questions. Well, how much load can this structure hold, and how much it will deform? For example, in aerospace, a wing may be strong enough and not to break, but if it bends too much, it ruins the aerodynamics. So we often have strict limits on displacement instead of strain, right? We care about displacement to make sure our structure is safe. Well, the problem is there is no single magic formula that directly connects force to displacement for every object. The relationship is messy. It depends on the geometry, the material properties, and how the object is held. So since we can't go directly from force to displacement, we need a systematic way to get there. This leads us to what I call the bypassing strategy. Think of this as a three-step bridge that connects the external world, force, right, to the internal world, materials, and back to the physical world, that is the deformation. Let's follow the map on the slide. The step 1 is from force to stress. We start with our load P. Using equilibrium, we convert that from external force to internal force, and we can calculate the stress using the internal force. Sigma equals P over A, right? The step 2 is stress to strain. This is where the material choice matters. We use our constitutive law. In other words, we use the Hooke's law, right? We convert stress into strain using, sigma equals E times epsilon. Remember, E here is Young's modulus if the structure is under tension and compression. And also, we can replace this E by the letter G, which is the shear modulus if we are deal with some shear problem, right? If you change the material from steel to aluminum, you simply change E and G, which changes the result, but the Hooke's law, the linear relationship, still holds, right? The step 3 is strain to displacement. Well, finally, we use geometry, right? We know strain is the change in length per unit length. So we're using epsilon equals delta over L, this kind of formula to relate the strain with real displacement, delta, the change in length. Now look at what happens when we combine these three equations. If we substitute them all together, replacing sigma and epsilon, right, we get one of the most famous and useful formulas in mechanics of materials. We get delta equals PL over EA. Remember here, delta is the change in length, or in other words, is the displacement, is the real-world deformation. And P is the real-world force applied, right? L is, the geometry. E is the material. A is still the geometry. Therefore, we have this kind of relation that can relate force and displacement directly, right? The equation is very powerful. It tells us exactly how to control the deformation. If you want less deformation, you just increase the area or pick a stiffer material. That means you increase A, right? Or you can make the bar shorter, which means you decrease the length L, right? But in most cases, the geometry is constrained, right? You cannot change the area and the length of the bar easily. Therefore, the best way to design the structure is to change the material. That means you increase the Young's modulus E, right? That's just a common engineering practice. Finally, we arrive at the most general form of the relationship. The formula we just derived is fantastic, but it has a major limitation. it assumes everything is constant. It assumes that the P is constant, the area A is constant, and the material E is constant. But look at the bar on the screen right now. Right? It's not, it don't have a constant area. The area is A is changing. It has a distributed load P, so the internal load is still changing. So how do we find the total deformation now? Right? We use the same three-step strategy, but here we need to use calculus. Right? It's no longer algebraic. We need to do the differentiation and integration. We follow the exact same roadmap from force to stress, from stress to strain, from strain to displacement, but we apply it to a tiny differential slice of length dx. When you combine this, you get the differential equation, right? To find the total deformation of the entire bar, we simply sum up the deformation of every single slice. In other words, we integrate from 0 to L, then we can get the total change in length delta equals like integration 0 to Ln over EA and integrate over the length, right? Let's put our new integral tool to the test using the drill pipe example we analyzed earlier. Recall that for the handing pipe, the internal force wasn't constant. It decreased linearly as we went down, right? So this is a recap of the results we got just now. Because the force N is changing, we must use the integral formula. We plug our force equation into the integral. When you perform this integration, you don't get a linear result. You actually get a quadratic equation. This tells us something fantastic about the physics. The displacement doesn't grow steadily. It follows a curve. If we evaluate this at the very bottom, namely x equals L at the very bottom end, right? We found the maximum stretch of the pipe is delta max equals W times L squared divided by 2EA, and this is actually the maximum or the total elongation of the pipe. Now we just plot the force, namely the AFD, right? We can plot the displacement also. We call this the actual displacement diagram, or in other words, it's called ADD, right? I want you to compare the two graphs on the slide, side by side. Okay, the AFD, the actual force diagram, on the left is a triangle. The internal force is linear. The ADD, the actual displacement diagram, on the right, is a curve. The displacement is parabolic. Why is it curved? Look at the slope, right? At the top, the slope is steep. That's because the stress is high, so the material is stretching rapidly. At the bottom, the curve flattens out to a zero slope. That's because the stress there is zero, so there is no local stretching happening. This diagram is the complete fingerprint of how the structure deforms. When we combine those concepts, we get three standard definitions that function just like a simple spring, right? First, the stiffness, denoted by K, equals EA over L, right? Think about the spring, right? F equals Kx. Here we also want to use this kind of a concept. Physically, the stiffness represents the force required to produce exactly 1 unit of elongation, right? Crucially, stiffness depends on length, right? A short bar is harder to stretch than a long one. So as length decreases, the stiffness decreases. Second is the flexibility, denoted by small f, equals L over EA. This is simply the inverse of stiffness, right? It tells us the amount of elongation caused by unit load, right? Finally, we have the axial rigidity, which is the product EA. This value allows us to talk about the strength of the cross-section itself. completely ignoring how long the bar actually is. Okay, that is the end of today. Before you guys head back out into the freezer, just a quick thought. Days like this really make you appreciate the warmth, don't they? Right? And I don't just mean the hater, I mean the people around you. Sometimes life gets cold, right? Figuratively speaking. And when it does, don't try to be a hero and freeze alone. Check your friends, check your notes, grab a coffee together. We are all stuck in this weather together, so let's look out for one another. Stay warm, everyone. Look forward to see you in the next lecture.